So yes, I'm Terence Broad, and my co-authors have already been introduced. I'm here to present our paper today, Active Divergence with Generative Deep Learning, a Survey and Taxonomy. So I'm going to start off by giving a very quick introduction to deep generative models, if people aren't aware of them. So deep generative models are deep neural networks that generate data, and they produce artifacts of high cultural value, and they're very prominent in lots of fields of research in AI, computer graphics, signal processing, and computational creativity. To train a generative model, the goal is to maximize the likelihood of generating the data, and in turn minimize the divergence between the training data, which is the target distribution P, and the approximate distribution P prime. So we're trying to get the divergence between these two distributions as close as we can to zero in the training procedure. So if we look at the network parameter view, we're starting from a set of randomly initialized weight parameters. And then over the course of training, we're trying to find the set of parameters that best approximate our target distribution P. And if we look at the distribution view, we have our target distribution P, and after training, we have our approximate distribution P prime. And this approximate distribution is trying to be as close as possible to the target. But obviously, on the right, we see these two overlapping, and there's always going to be some kind of divergence. So there's often modes of generation that are missing, but also our network might be generating things that lie outside of the true distribution. So what is active divergence? Well, this was introduced by my co-authors Sebastian Byrne and Simon Colton from a paper from last year's ICCC, and they define active divergence as any kind of method where we're actively diverging from the training data with generative deep learning techniques. And this is an important distinction to make because it's kind of an orthodoxy of machine learning, that we learn from data and we imitate data, and that's an end in and of itself. But I think in terms of creativity, there's a limited amount of creative potential if all you're trying to do is imitate data. So we think this looking at active divergence as a sort of different category of approaches is an important distinction to make. And these techniques have been advanced by computational creativity researchers and AI researchers, as well as artists and other practitioners who might be sharing their results on social media, things like Twitter, blogs, GitHub repositories, and we've made a big effort to make sure that we've given credit where it's due, regardless of where these advances have been disseminated. So we've surveyed all of these methods. I would if you want to get a full view of the survey, then you'll have to read the paper or watch our long presentation. But we've surveyed all these methods and we've grouped them together based on their underlying principles and tried to formalize them in this paper. So we've grouped them into 8 categories. And for the rest of the presentation, I'm going to give a quick overview of all of these different categories of ways of achieving active divergence. So the first is novelty search over learned representations. So here we would train a model in the normal sense, in the normal way where we're trying to imitate the data and minimize the divergence from the training data, but taking advantage of the fact that any generative model is going to have some degree of divergence. We can systematically search the learned representations that our model can generate, and then find the subset of those learned generations that are part of the approximate distribution P prime, but aren't part of the original training data, which is the target distribution P. So in the diagram, you can see this little orange shaded area where that's the subset that we've found through searching. And so there was this paper by Kazachi and others where they found digits that are not, so digits that aren't handwritten digits in the numerical 0 to 9, but still come from a model that have been trained on digits, so they look like digits, but they don't correspond to any of our existing categories of digits. The next category of methods in our taxonomy is novelty generation from an inspiring set. So here we're using a training data set, but we are not trying to imitate the data set per se, but use it as some kind of inspiration. But we're trying to train the model in such a way that it generates a novel distribution. So a good example of this is the creative adversarial networks, which takes inspiration from the GAN framework by Elgamal and others. And here they trained a network on images of paintings, and they were trying to maximize the likelihood of generating things that look like paintings but also diverge as much as possible from the existing style categories of existing styles of paintings. So here in our diagram, you can see how it's kind of trying to fit the overall distribution, but still diverge from any of the existing categories that have been labeled in the target data set. The next category in our taxonomy is chaining models together. So this is something that is done very commonly by artists who use generative models in their practice, but isn't documented very much in the academic literature. So just to give an overview, artists will often train generative models on custom data sets. They might go through lots of iterations of training models until they're getting results that they like, and then they'll train lots of these models together into sort of very esoteric combinations that will end up producing something that they find interesting results. So you might start with an unconditional generative model, such as a GAN, which takes random noise and generates some kind of generated output like an image, and then you might have translation models. So in the image domain, you have things like pix2pix and cycleGAN, and they might chain lots of these translation models together to produce more and more interesting results. And also things like style transfer and super resolution may be utilized. So a pioneer of this was the artist Helen Nasarin, and these images you can see here show some of the really arresting results that you can generate using this method. The next category in our taxonomy is training without data. So here we're starting with a model with randomized parameters, and then we're training it in such a way that we're learning a new set of parameters that produces a completely novel distribution. So if we're not using any data as a reference point, then we're almost certainly guaranteed to produce something that's novel. So we've broken this down into two categories. The first is relying on multi-generator dynamics. So this is some of my previous work where I again took inspiration from the GAN framework, but instead of having one generator trying to imitate data, I had two general networks that were trying to imitate each other. But they were also competing to produce the most colors compared to the other one in their generated outputs, and we ended up producing these quite simple compositions, but very colorful compositions at the same time. The other approach to this is generation via communication. We can think of this as communication via generation. So here he has one generator network that's generating images, another network that's recognizing images, and this he's getting, the generator is feeding it text vector embeddings of text, and then the other network has to try and reconstruct that. So they produce a generative language that's completely novel, but they use this for communication between the two networks. The next category in our taxonomy is divergent fine-tuning. So here we're starting from a pre-trained model that's already approximating a target distribution, but we're fine-tuning it in such a way that it's diverging from the original distribution or any other distribution that we can think of. So we've broken this down into four categories. The first is cross-domain training. So here we're starting from a pre-trained model and performing transfer learning, something which is commonly done for efficiency. And what a lot of people who were experimenting with transfer learning with the StyleGAN model of faces was that halfway through you would get this really interesting blend of the two data domains. So the model was producing this kind of hybrid of the two distributions. So here we've got an example that's starting from faces and it's being transfer learned onto images of beetles, but halfway through you get this kind of hybrid of faces and beetles. The next is continual domain shift. So the artist Nalson did a similar thing where he's doing transfer learning, but here he's constantly changing the target. So you've got this continually shifting domain that you're transfer learning to. And an interesting thing that he did was he would take samples that were produced by the generator and put that into the target distribution. And that was a way where he was able to kind of control the training process and in a divergent fashion, in a way that he found interesting. And I think that's a really interesting way of potentially controlling the generative process going forwards. The other two are infusing external knowledge. So there was a project called the StyleGAN NADA framework, where Gal and others fine-tuned a pre-trained model with clip. So people would have text in, would get a text embedding, so you could go from faces, and then you'd say, I want these faces to look like cubist paintings, and then it would change the weight parameters such that everything it generated were like faces that had the aspects of cubic painting. And then in some of my work is previous work is loss hacking, where we are where I fine-tuned a pre-trained model with the inverse of the adversarial loss function. So we're trying to make the images look as fake as possible rather than as real as possible, and we end up producing these really uncanny results. The next category in our taxonomy is network blending. So this gives us more control over blending two different data domains. So we take two models that are trained on different data domains and then blend the parameters together in some way. Sorry, this is a bit slow to load. One thing to note is that this only really works if the models have been transfer learned from the same original source. But because with StyleGAN, it's so expensive to train a model from scratch, everyone was training models from the original FFHQ model of faces, and people start to realize you could interpolate on these and get very interesting control over the domains. So here, this is an example of 5 different models that are being interpolated between, and you can see this sort of results. Come on. Sorry. The other approach of network blending is layer swapping. So instead of blending all of the parameters together, you can swap layers in and out. So this is an example of, we've got the original faces model of StyleGAN, and then we have a model that's been trained on a dataset of ukiyo-e images. And then if we do this layer swapping method, in the middle you can see that we're using higher representations from the ukiyo-e, but the lower representations from the StyleGAN model. So you get the spatial formation of ukiyo-e, but then the textual qualities, photographic textual qualities of the original model. And in D, then we do the opposite. So we've got the spatial formation of photorealistic images, but the textual qualities of ukiyo-e images. So this is a different way of combining these models together. The next category in our taxonomy is network bending. So here we're not making any changes to the weight parameters of the model. We're just inserting new layers that perform deterministic filters onto the internal representations of the model. And by doing this, we then produce new distributions because we're doing it inside the network. So this has been implemented for multiple domains. So I presented this work at Evo Muzart earlier this year. We did this work on images, and it's also been done in the audio domain by my colleagues at CCI and Goldsmiths. And as you can see, by applying different transforms in different layers of the network, we get very different results. And you can also analyze the models and group the features together based on similarity, and then you can group them together and transform them, and then you can transform semantically meaningful components of the model at the same time. The final category in our taxonomy is model rewriting. So here we're just making targeted changes to some of the weight parameters of the network, but not all of them. And you may only make very, very small changes, but that's enough to completely change the output distribution of the model. So we've broken this down into 2 different approaches. So the first is stochastic rewriting. So Mario Klingerman, in a series of artworks called Neural Glitch from 2018, he took pre-trained models and he started to manipulate the weights. So he would delete them or swap the values around or invert them and then see what it produced. And he produced these very compelling images. You can also do this in a more targeted fashion. So Bao and others from last year, they presented a paper called Rewriting the Rules of a Generative Model. And here they presented an interface where a user would copy and paste one aspect onto an image. So they would say, for example, I want the tops of churches to look like trees. So they would copy and paste like a Photoshop type interface. And then the model would then be optimized just on that one image to copy it. And this would then change the rules inside the network so that now every single church spire is being replaced with trees. So that's the overview of our taxonomy. I'm just going to quickly go overview. We see some of the applications of this for novelty generation. Obviously, there's a big potential for this to be used in creativity support tools or co-creation frameworks. And we think novel recombination is a really important aspect of this. So being able to adapt generative models to where we don't have very limited amounts of data that we can't train a model on, or no data at all. And so we think this is an interesting thing going forward. And then for future research, if there were quantitative methods where we could evaluate these methods and compare them, that would be really useful. And then in terms of furthering active divergence methods, we think multi-agent systems and open-ended reinforcement learning could be very fruitful in future research and hopefully lead to more autonomous creative systems using deep learning. So thank you for listening. You can contact me via email or on Twitter @TerryBroad, and I'm happy to take any questions now. Thank you very much.